Hello everyone and welcome back. So this time we're going to be going through dimensional analysis. Woo! Now that might sound really scary, but it's not. So let's jump into it. Okay, now what is dimensional analysis? It's simply looking at the dimensions of your equation and saying, can I solve this? Or looking at the dimensions of some quantity and figuring out what is it doing. For example, let's say you have no idea what velocity was. You're measuring velocity. And you're just like, okay, what is this weird velocity thing? But you know the units. They tell you, oh, it's meters per second we're measuring. So if you wanted to, you could go over here and you see, well, okay, meter is length and seconds, well, that's time. So this velocity thing is length over time, okay? Some sort of relationship between length and time. And there you go. You have just a little bit of information. And from that, you can also say, okay, well, if velocity is length over time, then any other unit that has dimensions of length over time should also be velocity, like mile per hour. Miles, length, hour, time. There you go. What about feet, hours per meter second squared? Okay, foot hours per meter second squared. Terrible handwriting. Sorry, don't usually write on here. Well, if you look at this, what you would normally do is you say like, okay, well, length and time on the top and length and time squared on the bottom. And you look at it, you cancel everything, and what you see is that this is just 1 over time. So that is not a unit of velocity. So you can look at this through dimensional analysis and say, okay, what am I actually looking at, even if it's super complex like that? Another little example is, what about Newton meters? And this is where you probably get confused because you're like, Newtons? Fig Newtons? They're delicious, but what do they have to do with engineering? Not fig Newtons. This is actually a unit of force. So this would be force right here. But force is not a fundamental dimension. Length is. So we have to figure out what the fundamental dimensions are that are making this up. So that can help you. Another thing to think about is that even if something has the same dimensions, like in this case, force times length, it's not necessarily the same thing. You can have units of, like for example, torque, like trying to twist the lug nuts in your car tire, and energy actually have the same units, but they measure completely different things. So it gives you some information, but don't take it too far. Okay, so like I said, force was the dimension of a Newton. Newton measures force. But force is not a fundamental dimension. It is something called a derived dimension. Now, for a derived dimension, you have a derived unit, or in some cases, a named unit. Derived dimensions are any time we take our fundamental dimensions, which are length, time, mass, and temperature, and there's a few others which we don't use that often, and we multiply or divide them all together. So length over time, that's velocity. Velocity is the derived dimension. Length and time are our fundamental dimensions. Length squared, that's area. Area is our derived dimension. Length squared is our fundamental dimensions. Okay. Now, you're probably wondering about this whole name thing. Derived might make sense. Okay, it's a made-up unit. It's a mixture of all those other little base units. What about named? Well, named units are when you're really super famous and amazing, and they decide, you know what? Instead of calling it what it is, we're going to call it something after you because you're awesome. Hopefully, all of you will have your own named unit one day. I do. Just by being named, luckily. There's something called a gray. It's a unit of like radiation exposure. Probably not a good unit to have named after you, but I'll take it. I'll take it. It's my unit. Okay, so the Newton is a unit of force. Isaac Newton, apple falls on his head. Force. But force is a derived dimension, and the Newton is a derived unit, and it's made up of base units, which are kilograms, meters, and seconds squared. We will have so much practice with converting kilogram meter per second squared to a Newton. They're the same thing. If you see one, you see the other. And then we have Pascal, which is a unit of pressure. Joule, a unit of energy. Watt, a unit of power. And pound, a unit of force. If you're like, oh, this is going way too fast here, don't worry. We have an entire unit with each of these. 4 right here. One with this one, this one, this one, and here. Now, pound and Newton are both units of force. Now, what almost no one in the United States probably knows is that pound is a derived unit. It's made up of slug feet per second squared. There's a symmetry here. Mass, length, over time squared. So you see that they're the same, just different units. A pound is by no means, though, equal to a pound mass foot per second squared. That is wrong. Don't do that. If you're trying to make a pound from a mass and acceleration, it has to be slugs and it has to be feet per second squared. But better yet, just convert everything to metric and then convert to pounds at the end. That's the safer way to do it. And you'll get practice with that in, I think, Unit 15. We'll see. It's going to be great. Okay. Now with this, just another little note that there are way too many named units. So this is not a full list. Okay, it's not a full list. This is just the ones we're going to hit on the most commonly in this class. Now, I hope this helped you, and I will see all of you next time as we learn some other fun stuff you can do with dimensional analysis. See you later. Bye-bye.